Hi, my name is David Ho, and I work for the Hydrologic Engineering Center in Davis, California. This video series is part of the basic HEC-HMS class discussing surface runoff. We will be going over the Clark unit hydrograph, which is one of the synthetic methods available within HMS. In a previous video, we discussed how to derive a unit hydrograph from a recorded discharge gauge. For the synthetic method, we derive a unit hydrograph for a basin using theoretical or empirical formulas that relate the discharge peak flow and timing to its watershed characteristics. One of the original intents for using the synthetic method was for modeling ungauged watersheds, where you do not have a recorded discharge. Instead, you develop the unit hydrograph based on the watershed characteristics. The principles and assumptions of unit hydrograph theory still remain the same, but the development of the hydrograph is based on a function of one or two parameters. Synthetic methods are not limited to only ungauged basins and are used in gauged or ungauged systems to estimate surface runoff. Synthetic unit hydrographs make use of the instantaneous unit hydrograph, which is the runoff response that would result from an instantaneous unit input of excess rainfall. This allows you to construct a unit hydrograph that can be applied to any duration rainfall and not constricted to a specific rainfall duration. In HMS, there are three methods available: the Clark, SCS, and Snyder's method. This video will look at the Clark unit hydrograph method, as well as briefly talk about the mod Clark. The Clark model derives a unit hydrograph by representing two critical processes, that of translation and attenuation. So translation is the movement of excess runoff to the watershed outlet in response to gravity. Translation in the Clark method is modeled using the time area curve, and the critical parameter to estimating translation is the time of concentration. The second process is attenuation, which is the reduction of the discharge magnitude due to frictional forces or storages within the channel or basin. The attenuation effects are modeled using a linear reservoir, and the parameter that controls attenuation is the storage coefficient. So this slide illustrates the two processes modeled in Clark. You create a time area histogram by discretizing your watershed regions based on the time it takes for runoff generated on that area to reach the watershed outlet. We call the contours that delineate those regions isochrons. You can develop a time area histogram that graphs the regions with equal travel time to the outlet with the associated area. So in this graph, you may have noticed a Q on the y-axis, which stands for discharge. This is because the area was multiplied by a rainfall depth and divided by the time, but essentially looks the same as a time area graph. So once you've determined your time area relationship, the second process is to have the runoff carried out by a single linear reservoir to get your instantaneous unit hydrograph, which we mentioned isn't confined to a specific rainfall duration. The next few slides will go into more detail on the time area relationship and the linear reservoir. So we noted that the translation process was governed by one parameter called the time of concentration, which is defined as the hydraulically most distant point with the longest travel time to the watershed outlet. So you can imagine a raindrop at the most remote part of the watershed and the time it takes for that raindrop to travel through the watershed to the outlet. So there are various methods out there that try to estimate the time of concentration from the basin characteristics. One of the most popular ways is the TR55 method, developed from the US Department of Agriculture. Another method of estimating the time of concentration can be to use region-specific regression equations. The time area relationship governs the translation portion of the hydrograph. This relationship divides the watershed into regions of equal runoff time to reach the outlet. Once the areas are divided, estimates of the runoff generated on each part of the catchment is delayed by a proportion of the time of concentration. The examples you see are time area graphs for three different watershed shapes, where each line represents an isochron. The time area relationship is expressed in the dimensionless form, where area as a percent of total basin area and time as a percent of the time of concentration. This is where the time of concentration parameter comes into play. If you increase your time of concentration, you increase the amount of time it takes for each of your isochron regions to reach the watershed outlet. If we use the rectangle watershed shape as an example, the first region in the rectangle is closest to the outlet location and would appear first in our time-area relationship. The last region in the rectangle, which is equal to the time of concentration, would appear last in our time-area relationship. As you noticed, the time-area relationships can vary based on watershed shape. The default in HMS utilizes this generalized oval-shaped pattern. Attenuation takes the time-area results and reduces the flow by routing it through a single linear reservoir model. The linear reservoir concept is that the watershed behaves as a reservoir in which storage value S is linearly related to the outflow and a constant value R, where R is the storage coefficient. For other linear reservoir methods, you might see the storage coefficient as K. Using the continuity equation and a finite difference approximation, you can solve for the outflow ordinates. The storage coefficient is a coefficient that represents the temporary storage of precipitation excess in the watershed as it drains to the outlet. The greater your R value, the more time your excess runoff remains in storage. In contrast to the time of concentration, which has a definition that can be physically quantified, the storage coefficient is a bit more nebulous. There is a way to relate the storage coefficient mathematically to the observed hydrograph as the volume of the hydrograph divided by the slope of the inflection point on the hydrograph recession limb. But the easiest way to estimate R is through calibration if gauged precipitation and stream flow data are available. R can also be estimated through empirical equations that have been developed through regression analysis. So this figure shows the discharge after it has gone through translation from the time area curve. This was assuming a default watershed shape, a constant velocity, and 1 inch of rainfall over the watershed. You can then see the results of the discharge histogram after getting routed through the linear reservoir, resulting in the final unit hydrograph for using the Clark method. You can see the effects of routing through the linear reservoir as the peak flow is decreased and the time base for the hydrograph is spread out. There is a variation to the Clark unit hydrograph method that can transform rainfall to flow on a grid cell basis, and that is called the Mod-Clark unit hydrograph method. The Mod-Clark method is a linear quasi-distributed transform method that is based on the Clark unit hydrograph. The Mod-Clark represents the subbasins as a collection of grid cells. You still need to estimate the time of concentration and storage coefficient, but the advantage between the lumped method and the Mod-Clark method is that the Mod-Clark eliminates the time area curve, instead uses a separate travel time index for each grid cell. So before, you would need to come up with your own time area curve or use the default relationship. Now, there is in a sense a unique time area relationship created for each watershed that gets generated automatically when applying this method. There is a travel time index computed for each cell that represents the travel time from the cell to the watershed outlet and is scaled by the overall time of concentration. You can get a discharge value per cell based on the cell area, excess rainfall depth, and the cell travel time. The cell discharge still gets attenuated by the linear reservoir. The outputs from the linear reservoir of the cell are combined to produce the final hydrograph, which you see in this figure. This method is quasi-distributed, meaning that we can spatially account for the flow transform for each grid cell, but this method does not route the discharge from one cell to the next, hence why we call it a quasi-distributed. To implement the Clark unit hydrograph method in HMS, you'll need to first select a subbasin, or your watershed. Head down to the subbasin component editor and select Clark unit hydrograph in your transform method. Navigate over to your transform tab and enter your time of concentration and storage coefficient values. You'll notice that under method that there are 3 available methods that you can select: standard, variable parameter, or the Maricopa County. Select the standard method for the regular application of Clark unit hydrograph. In this tab, you can also enter your time area method. You are given a default value, which uses a generalized semi-oval watershed shape. The default shape has been shown to approximate the timing of the surface runoff very well for typical subbasins. However, there is still the option to provide a user-specified curve. The relationship must be defined as a percentage curve in the paired data manager before it can be used in the subbasin element. To do that, head over to your components menu and click on the paired data manager. Under the data type, select the percentage curves. Click New to add a new percentage curve. In this example, I have already created one called Rectangle. Once you've created your paired data, head down to your paired data folder and expand the percentage curve and select the item below. You can add your percentage curve either through the DSS or you can enter it manually. By selecting manual entry, you enter your values in the table. The left column represents the percentage of your time of concentration, and the right column represents the percentage of your drainage area. Both should be increasing up to 100%. Once you've created your own time area relationship, navigate back to your subbasin, Component Editor tab, Transform, and add your percentage curve. Thank you for listening to the Surface Runoff video series. Visit our website to learn more about how to use HMS and follow future updates. See you in the next video on the SES dimensionless synthetic unit hydrograph method.